Ready.
Good morning. In this project, we analyzed the hydraulic performance of a centrifugal pump using computational fluid dynamics or CFD. Centrifugal pumps are the widely used in the industry due to their reliability and efficiency in the liquid transport. In this world, a centrifugal pump operation that 29 HTRPM was designed and analyzed. The geometrical was first created to in Autodesk Inventor and later simulate in Star CNC M+, using and mesh approximately one that 37 million cells. Finally, 20 simulations were performed 10 with water and 10 with mineral oil in order to evaluate how fluid viscosity affects head efficiency and internal flow behavior. In the literature review, CFD in the pumps, the CFD is widely used to predict pump performance before building physical prototypes. It allows engineers to analyze velocity fields, pressures distributions, and internal flows partners inside the impeller and the volute. Additional CFD helps identify hydraulic loss, recirculation zones, and cavitation phenomena that strongly influence a pump's performance. Because of this advantage, CFD has become as a started tool for analyzing centrifugal pumps. Uh, in this case, pumping of viscous fluids, fluid viscosity as significant important on the pump performance, as viscosity increases hydraulic losses inside the pump also increase, which are reduce both the head and efficiency. In addition, the best efficiency point tends to shift to lower flow rates when pumping more the viscous fluid. For the reason, CFD simulation are very useful for studying pumps performance under different fluid conditions. In this case, the cavitation, another important phenomenon in the centrifugal pumps in the cavitation. Cavitation occurs where when the local pressure drops below the vapor pressure of the fluid, forming bubbles. When these bubbles collapse, they can cause noise, vibration, erosion, and efficiency losses. CFD models help identify regions where the cavitation may occur and analyze how the pump geometry affects this behavior. Mm,
For the methodology, we were giving a pump designed by Grundfos, and we were designed to make it ourselves, doing very small variations with the angles. For this, we use turbo machinery design relations to be able to get all of the values of the velocity triangles, as well as the diameter of both the impeller and the entrance and the exits of the volute using the table you see before you. With all of the values calculated, were we transferred all of those into polar coordinates, making it very easy and simple to make a graph and very specific points of both the volute and as well as the impeller blades. These coordinates were then transferred to the 3D modeling program Autodesk Inventor to build all of the to build the impeller, the volute, and then the rotational zone.
The geometry was designed using turbomachinery design relations and velocity triangles analytics. These velocity triangles define the relationship between the different velocity compounds at the inlet and outlet of the impeller. Using these parameters, the impeller blades were generated in the full 3D model of the impeller and volute was created in the Autodesk Inventor. The design used backward curved blades and volute design according to Gulich proportional and the growth criterion. After creating the CAD model, the pump was simulated in Star CNC M+. A computational mesh was generated to represent the fluid domain. In this case, a coarse mesh was selected to reduce computational costs while maintaining accuracy. This numerical model allow used to simulate the internal flow and evaluate the hydraulic performance of the pump.
The operational conditions that we decided to take were constant temperature as well as density to make the fluid more simple to design. Since we are using both water and oil, we needed to test them in equal properties. The reason we took K epsilon is we wanted to measure the friction or the losses caused by the friction in both the total head, the velocity, and the brake power and the hydraulic power. We chose steady flow, so the time wouldn't have anything to do with the pump. It had no relation. We also chose a mesh base size of the exit of the volute, and we had a minimum soil requirement of 1,200,000. The mesh independence shows the grid actually converges when the number of cells increases from 1,240,118 to the fine one. The head and efficiency remain constant. This indicates the mesh is in fact independent. The average Y plus stays stable at approximately 1.5 across all mesh levels, and the grid convergence index is around 0.05 and 0.06, which suggests that numerical uncertainty related to the mesh is completely negligible. Here, the graphs show the water total head MSE on the left and the efficiency MSE on the right. On the left, you can see that the computational power increases, or the computational time increases a lot, while the error also increases, and as well as on the efficiency. So we decided to take the mesh in the middle, which was the normal mesh. Here you can see the manufacturer's curve utilizing water and the simulation that we obtained utilizing water. The brake power and the hydraulic power curves are similar, getting to similar points with a similar curvature. However, the total head increases or decreases much faster, it reaches a much lower point and at a much lower flow.
RMS analysis to evaluate the accuracy of the simulation at the road main square analytics was performed. The graph compared the CFD results with the manufacturer data. Most points fall within the plus the 10% error range, indicating that the simulation results are the rationality accord. This supports the ability of the CFD model.
For the velocity profile, we can see the fluid going in the direction it's supposed to, rotating around the impeller, going out the volute. However, it is non-uniform in the tongue, producing the hydraulic loss. Also, one can see the low velocity profiles on the backs of the impellers, which can turn kinetic energy into pressure, which will be discussed further. However, the flow of the water stabilizes in the discharge pipe. The pressure profile shows there will be cavitation since the pressure of the pump is lower than the water pressure or the vapor pressure of the water. It will get to boil right in the eye of the impeller, which means there will be some modifications needed for this to be a viable design. However, the pressure rings are uniform and concentric around the whole impeller. Now, as to the wall Y plus, there are very low Y plus values across all of the impeller on both the blades and the shroud, which means the K epsilon model will have a lot of an easier time running and simulating everything, and it is fine enough to resolve boundary layers without needing any extra steps. In conclusion, we can see that CFD simulations are very viable and they do actually give the expected performance that one would need from a centrifugal pump. The reference curves shown in the simulation and the observed ones, the manufacturer's ones, were similar enough for it to be considered viable.
And
Also, oh, go ahead.
Okay. In addition, the results showed good agreement with the reference performance curves. The study also demonstrated that the fluid viscosity significantly affected pump performance, reducing efficiency due to the higher viscous losses. The maximum efficiency obtained was approximately 20, no, 74 percent with water, while efficiency decreased to around 55 percent and 60% with mineral oil. Overall, the result compared to the CFD is a powerful tool for analyzing and optimizing centrifugal pump design.
Thank you for listening. These are our references.